Okay, so we complete the chapter 4, right? In chapter 4, we learned about the process architecture. And then I mentioned that this topic is very important. So actually the pipelining is so critical. Actually, you need to understand the concept of a pipelining. Also, so you need to understand the performance issues in the pipeline, the architecture. And then also you need to understand how to handle these performance issues in of the pipeline architecture. Okay, so this is very important. And so now, so we are in the chapter five of the textbook. So we will learn about the memory systems. Uh, the memory system is also the very important part in the computer systems. So it is because our data are stored in the memory systems, and then actually the processors read our data from memory, and then processors execute instructions, but the purpose of those instructions is processing our data. So by processing our data, these instructions generate the processed result, right? Computed result. So the data actually, so you can understand that a computer is a machine that computes data, right? That process data, okay? Actually the binary data. And then because these data are in the memory, and then also the memory performance is very critical for the performance of our computer system. So we learned about the stored program computer, and then so actually we learned that all data, our normal data and the instructions are stored in memory. Okay, so so and then processors read data from these data from memory, and then processors execute instructions. But when we learned about the RISC-V instructions in chapter 2, so we just learned that there are only two kinds of memory instructions, right? Like the load instructions, like load word, or load double word, and then also we learned about the store instructions. Actually, in RISC type instructions, RISC type CPUs use these two kinds of memory instructions. So you may think that RISC-V just has only several instructions that can access the memory. So you may think that the memory instructions are not critical, are not important, but it's not true actually. So in order to compute our data, actually using these load instructions, a computer fetch. So fetch means that it transfers data from memory to register. Okay, it is the meaning of the memory fetch, right? So a computer fetches data from memory, right? Using the load instruction. And then if the data are loaded into the register file, the computer can execute normal instructions like arithmetic, logic, and some other instructions, right? And then the computed instructions are also stored in the register file, and these computed results are also transferred to the memory, right? Then what is the memory performance? So we learned all data are in the memory, right? And then so where is the memory? Then in this figure. So So we can equip a CPU in in this CPU slot, and then also you can observe the DIMM slots. Okay, it's called the DIMM. Okay, it's a DIMM. Okay, so actually DIMM is the kind of memory module. Okay, so we can also attach the DIMM modules in this DIMM slots, and then CPU access this DRAM. Okay, it's external memory. So this is the physical computer board, and then in the physical computer board, we can observe the memory slots here, and then also the CPU accesses data in this external memory, right? Then where are memories in the processor architecture? So we learned about the processor architecture in chapter 4, right? So where are memories? So you can find that this is the instruction memory, and then this is the data memory, right? In chapter 4, we learned that the memory is a split, right? So it's split into instruction memory and data memory. So why? In order to avoid structure hazard, right? So in order to avoid, in chapter 4, we learned about the hazards, right? And then actually we split the memory into the two different memories, like the instruction memory and the data memory, to prevent structure hazard. But when I explained about this structure hazard, I mentioned that this is actually these memories are not actually main memory. It is cache. Okay. So this is the cache. So in chapter 4, so we learned that these are instruction memory and data memory and memory instructions such as load instructions and store instructions access data memory. Also, in order to fetch data from the memory, the CPU accesses instruction memory, right? So that's what we learned in chapter 4. But actually, these memories are caches. So, and in chapter 5, so we will learn about the caches, okay? Cache memories. So then we can understand the processor model like this, okay? So as you can see, the computer system, this is kind of a very simplified model of the computer system. And then as you can see, you can find the processor here, and then the memory is here. So in a computer system, a processor and memory systems are the main components in the computer system. So this is because the computer is a machine that processes data in the memory. Okay, so all data are stored in the memory, right? So we can understand the computer system. So as I mentioned, it's a very simplified model, right? But we can understand the computer system like this. So what can you observe? So this is the processor, and then this is the memory, and then the processor is synchronized by clock signal because the processors are also the digital system, and then also the memory. The memory is working with the clock signal, right? So because the memory is also the kind of digital system, right? And the processor gives commands, the memory commands. So in this example, you can find the write enable signal and address and write data. So actually, This write enable signal and write data are required for write operation, for store operation, right? And then the address. The address is given to the memory. So also the memory provides the data, the requested data, right? Request data are given to the processor, and then processor received data, and then processor compute these data, right? So the performance. So I mentioned that a processor and memory systems are the main part, the main components in a computer system, and which means the performance of processor is very important, is critical. Also, the performance of memory is also critical for the performance of entire computer system, right? Then, so we learned that the computer process, the performance of a processor is determined by execution time, right? Because the performance is the inverse of the execution time. And then this execution time is defined as the instruction count multiplied by CPI multiplied by TC. Then how can we define the performance of this memory, the memory system? Also, time. So we can define the time. And how can we define the time, the elapsed time by this memory system? Then, so I mentioned a processor gives request. So it's a request. So this request is, so there are two kinds of request, the read request and write request, right? The requests are given to the memory. Then based on the given request, the memory provides the result, okay? It provides services, right? So the store instruction, the memory can just store the data, right? But the read instruction, read request, for the read request, the memory needs to provide the data to the processor. So, which means if the processor gives the read request, okay, it's a load, then after some time, the delta t, then memory provides the requested data to the processor. And then so you can find the delta t. So it is the time between the request, the request from the CPU, and then the response. Response is the data from the memory. And then we can define this time as the performance. So, and then obviously the performance is the inverse of this time, the response time of this memory, right? So we can define the performance of memory is the inverse of delta t. Then in order to improve the performance, so then why the performance of computer system is also determined by the performance of the memory system. So it is because if you observe the normal code, so normal the program code, you can find many load instructions. Okay, and then load instruction fetch data from the memory. So if you read the compiled code, right? So you can generate the compiled code by using the compiler, GCC compiler, right? And then if you observe that is compiled code, then you can find the many load instructions, and then after that, no more arithmetic or logical instructions actually use the data fetched by load instructions, right? So actually you can find the data dependencies between load instruction and following arithmetic instructions. So if this delta t is long, okay, delta t is high, then actually the following instruction, these following instructions cannot be executed, right? It's a kind of a data hazard, right? So because the following instruction can be executed after the data is loaded into the register file, right? Do you understand? So that's why the memory performance is also very critical. Okay. But problem is that memory is much slower than the CPU. So that's the problem. Uh, so you may think that GPU is very fast. It's because the CPU is the kind of digital system, and then in order to the CPU performance is defined by CC, and then in order to improve the performance, we need to reduce the clock period. So which means we can increase the clock frequency of the CPU. So it means the fast CPU. So you may think, oh, so CPU is also the kind of a digital system, and then in order to improve the performance of a digital system, then we can increase the clock frequency. And then now the clock frequency is around the up to 4 to 5 gigahertz for the desktop CPU, right? So you may think, oh, memory is also kind of a digital system. So we can also increase the clock frequency like the CPU, right? But actually, think so. The semiconductor processes for CPU and semiconductor manufacturing processes for memory, so especially DRAM. So these technologies are different. So for the CPU, we use the logic processes, and then for DRAM, we use the DRAM processes, right? And then it's totally different. Also, actually uh, the memory stores the electric charges, okay? And then based on this amount of electric charges, so we can just identify the values stored in the memory cell. But it's kind of actually all these all circuits are analog circuits, okay? But the performance of the memory is determined by the characteristics, also the design, the the design approach of the memory. Also, it means it is determined by some manufacturing processes for memory design. Okay. So problem is CPU is fast, but memory is slow. And then our computer system, actually I mentioned the CPU and our memory systems are two main parts of the system, our computer system, and then the CPU interact with the memory system. But this part is slow. For the there are many main two parts, but one of the two parts is very, very slow. So what will happen? Overall system performance will be degraded, right? So, there are two components, and then actually in order to work So in order to operate the system, actually these two components need to interact each other, but one of the components is very, very slow. Then overall performance is also degraded. Okay. So actually we can observe the performance gap between the CPU and the memory. So actually this performance gap is called the memory wall. Okay. So memory wall represent the performance of a computer system is determined by slow memory systems. Okay. So this is bad news, right? Because so everyone wants a better computer system, right? And the better computer system represent the fast computer system, but our memory is very slow. And even though the CPU is fast, so memory is slow. So this gap is very high, very large. And then actually the slow memory systems decide the performance of overall computer system. Okay, so that's why the performance of a memory system is very critical for the performance of entire computer system. So we need to handle this issue. Okay, we need to handle this issue. Then how? How? So we use memory hierarchy. So this is the solution that can handle this memory wall, the performance issues by slow memory system. So, but before I explain about the memory hierarchy, I will explain about the data locality. So this is called the principle of locality. And then also this is very important. Okay. So locality. So what is the locality? What is the minimum of locality? So locality means that uh, actually, so this is the system, but in the overall system, we just access the some part of system resources or data repeatedly, right? So this is called the locality. Okay. So, so actually this is so in the real world, so we can observe the locality, right? So it is because of, so we are physically constrained, right? So for example, when we read a book, so actually we just to read we focus on the only one book or two or three books maybe, you know, short short time windows, right? So if you start to read a certain book, then actually we focus on this book in the real world, right? Even though there are many books in our library or in our study room, but we just focus on the only several books, right? This is also the kind of locality. So locality means that only the small amount of resources or data are repeatedly accessed within a short time window. Okay, so this is the definition of locality. Okay, then why this locality is important in the computer system? So it is because so I mentioned that the data, that all data are stored in the main memory, right? Main memory of a computer system. And then what's the problem? The problem is that, oh, this memory is very, very slow, right? But our program, our application, when we learn a certain application, then this application only access the part of data, right? And these small amount of data are actually repeatedly accessed. Then if we just complete the operation with this data, then we just focused on the other data chunk, okay, other data chunks. And then we repeatedly access this data, this small chunk of data in the memory. And then again and again. So our program is also designed like this. Okay. So so the like us, okay. So we can only focus on the a small the several tasks only in the short time window, right? So we actually the people cannot multitasking is very very uh, difficult, right? So actually, we need to focus on only on a small amount of resources or data or kind of books, right? Program is the same. When the program just access a small amount of data, even though a large amount of data is in the memory, but the program just access a small amount of data repeatedly. So this is very important. Repeatedly within a short time window. So the locality is observed in our programs. Okay. And then there are two kinds of locality. It's a temporal locality and spatial locality. So when we use the word temporal, so it means it's a time-based, it's a time, and then spatial, and then it represents the space. Then what is the temporal locality? The temporal means it's a time-based. So temporal locality means that if a certain data is accessed by a program, right? So for example, using the load instruction, we access this data. Then this data will be accessed again. The same data will be accessed again and again. Okay, within a short time window. So this is called the temporal locality. So temporal locality represents that the same data is repeatedly accessed, repeatedly used in a computer system. So you can find the examples here. So for example, the instructions in a loop. So I mentioned that the instructions are also data. Also, instructions are in the memory, right? And then if we use the for loop, like for, and then some statement here, then using this for iterative loop, these statements are repeatedly executed. Then what does that mean? Oh, these instructions are in the memory, right? And then the same instructions are repeatedly fetched again, right? So because this is the iterative loop, and then iterative loop repeats the same instructions again and again. So same data are repeatedly requested and used. This is the temporal locality. Also, if we use a variable, and then if these variables are repeatedly used, then we can say that, oh, we can observe temporal locality, right? And then we can find those many cases in our program. Okay. Then what is spatial locality? I mentioned that the spatial represent the space, which means uh, in the memory, if a certain data is accessed, then neighbor data, a program will access the neighbor data with a high probability. So this is the spatial locality. Then what is the neighbor data in our program? What does that mean? Neighbor data. We use address, right? In order to access the data, then we use address. Address means 주소, right? So neighbor data means using a certain address like ADDR, then we access the variable capital A, and then using the similar address but address plus 4, then we can access the neighbor data B, right? And then using also the address of 8, and you can access the neighbor data C. So if the address values are similar, then we can say that these are neighbor data, right? So spatial locality means that if a certain data is accessed, certain data are requested by our program, then with high probability, a computer will request the near neighbor data, neighbor variables. Okay, so this is the spatial locality. So, and then also we can observe the some examples. So you can find the examples here. Sequential instructions. So instructions are also data, and then we learned that in order to read the next instruction, we just increase the PC by 4, right? So this is the near data, the neighbor data, right? So one instruction is read, and then next instruction is read, but it's the address of this next instruction is the PC plus 4, right? PC and PC plus 4 and PC plus 8, like this. So neighbor data are accessed. And then array data. In the iterative loop, if we just access the array data, and then if the A0 is accessed, and then in the next turn, then we will access the A1, and then we will access the A2, blah, blah, blah. And then we already learned that in the array data, so actually we can just increase the offset of this uh, offset to access the next element in an array data, right? So we also observe very strong spatial locality. Okay, so these are characteristics of our normal applications. Okay, we can observe strong temporal locality. Also, we can observe strong spatial locality in our normal applications. And then based on these observations, we can handle the performance issues of a slow memory system using memory hierarchy. How? So this is the example of memory hierarchy. And then, so actually, this is the CPU, and then inside of a CPU chip, we also include the smaller memory. And then these memories are called caches. So I will explain about the cache later. Okay, so cache, and then also there is main memory, but this main memory is the external memory. So it's a large. The main memory is the DRAM, and then DRAM is large and slow. And then also we store our data in the, so you can find the hard disk here. So but recently we can use the SSD, but hard disks, HDD and or SSD are storage devices. So compared to the main memory, like DRAM, the capacity of a storage system is very high. It's a very large, but it's also very slower. Okay. So actually in a computer system, we use different kinds of memory devices. So in this example, you can find the cache, and then you can find the main memory, and then you can find the storage devices like hard disks or SSD. Okay. And then also we can observe these different memory devices exhibit the different characteristics, right? I mentioned, oh, DRAM is slow, but it's large. Hard disk or SSD, the capacity is very large, but much slower than DRAM. And how about the cache? Cache is a fast, but it's small. Okay. So actually we can observe different kinds of memory devices are included in our computer system, but these memory devices exhibit the different characteristics. And then by using these uh, divergent characteristics of the different memory devices, we can organize memory hierarchy like this. So what can you observe? R represent the register file, okay, registers, and these are caches, okay. So you can find the L1, L2, L3 caches, and then usually the caches and then register file are included in the CPU chip, okay. So CPU package, and then main memory is the DRAM, and then storage is the SSD. You can use the SSD or HDD, hard disk drives, as the storage devices. And then also you can find the characteristics of different memory devices. Register file. So register file, the cost is high. So what does that mean? In order to use, in order to build these register files, then how do you cost? The manufacturing cost is very high. Also, the the register file consumes high power. Okay, but when we consider the performance is very high. So what does it mean? It's fast. And what's the definition of the speed or access? So this is the access latency. So I explained that performance of the memory system is, so request is given, the request is given, and then the memory system provides the response, memory system responses to this request. So, and then we can observe the delta t delay. So I mentioned this delta t determines the performance of memory devices, right? So then what is the high performance? High performance means that this delta t, the response time is small, it's a low, right? So it's very fast. Capacity, small, okay? It's a low capacity. So you can observe that these memories like register file and caches, capacity is small. So it's a small memory, but it's fast memory, okay? And then usually if the memory size is small, then we can say that this memory is faster, okay? Smaller memories are usually faster, okay? So it is also determined by memory technologies, but usually if we build the smaller memories, then these memories are fast. How about these memories, like the main memory or storage? Cost is low, right? It's cheap, okay? And then, but also the performance is low. Capacity is high. So what does that mean? We can store the large amount of data in the low level memory devices like storage, right? So we can store our old data in the SSD or hard disk drives, but it's very, very slow, right? So we organize the memory systems like this. And then where is the CPU? CPU is here. Okay, the processor is here. Then why? How can we handle the performance issues of slow memory using this memory hierarchy? Because of locality. So what does that mean? I mentioned our program actually. So even though our program accesses the large amount of data, but within a short time window, okay, within a short time window, our programs will access the smaller amount of data repeatedly, right? Then this small amount of data can be stored in the smaller memory, but this memory is fast, right? Then what is the benefit? Our program will access this data repeatedly, right? It's more frequently within a short time window, right? But this smaller amount of data are provided by faster memory. Then because the size is small, we can store this small data in the smaller memory, right? And then so these data are frequently provided by this fast memory. Then we can reduce the response time from the memory, right? Do you understand? So delta T is reduced. So even though the data size is very large, but only the part of data and these data will be frequently requested, frequently accessed. This smaller amount of data are stored in the smaller memory, like caches. Okay, then we can access this data very quickly. So by doing this, we can improve the performance of memory system. Obviously, right? Do you understand? So that's why the locality. So firstly, we need to understand about the locality of our data. Okay, we so our program exhibit the very strong temporal and spatial locality. So which means only the small amount of data is repeatedly accessed within a short time window. So within this short time window, we can store this small amount of data in the smaller memory. And what this is, so the smaller memory is close to the CPU. Then CPU will access this smaller amount of data frequently. Okay, and then the performance is high. The performance of this small memory devices is high. So we can reduce the response time. Okay, this is the benefit of memory hierarchy. So we can exploit we can utilize the memory hierarchy because our applications exhibit very strong locality, right? So this is very important. So because our applications exhibit the very strong data locality, then we can utilize the memory hierarchy. What does that mean? If our applications do, do not exhibit strong data locality, then performance will be also degraded. Okay? Because of these properties, we can utilize the memory hierarchy. And then this is called the memory hierarchy. And in Korean, it's called the memory 계층 구조. It's a memory hierarchy because this is the higher level, this is the higher level, this is the low level. Okay. So this is the low level and this is the high level. And then higher level memory is located close to CPU, right? And then also the memory devices in the higher level, the performance is high, but the size is small. And then you can understand that smaller memory exhibit the higher performance, right? And then the memory devices in the lower level, then the performance is low, but the size is large. Okay, we can store a large amount of data in the lower level memory. So this is the memory hierarchy. Okay, so in chapter 4, so we just learned that this is the process architecture in chapter 4, right? So in chapter 4, I did not explain about the memory hierarchy, right? So we just assume that there are only one level of memory devices like instruction memory and data memory, right? And then we assume when the load instruction is accessed, then we assume that this load instruction can find the requested data in the data memory always. That's our assumption. How about the instruction memory? So I mentioned this is also the memory, but when the instruction is fetched, then we assumed the requested instructions are found in the instruction memory always. Okay, that's our assumption in chapter 4. But we learned about the memory hierarchy. Actually, our computer system utilizes the memory hierarchy. Okay, so which means these caches are the size of caches or the high level memory is small. So what does it mean? The size is small. If the memory size is small, then these memories cannot store entire data. And what does that mean? We can find the request data in the memory, or we cannot find the requested data in this memory because the size is small. We cannot store entire data in this smaller memory. Do you understand? And then I mentioned that these are actually caches, right? It's not main memory, it's the caches. Okay, so it's a small. It's small, and actually we cannot find all data. We can all we cannot store entire data in these caches. Actually, instruction memory is the instruction cache. Actually, level 1 instruction cache. Data memory, this is the level 1 data cache. Okay. Then what does that mean? Actually, when the memory instruction is executed, these memory instructions work like this. So it's a CPU. Firstly, it's a level 1 cache. Okay. CPU firstly access level 1 cache. Okay. So for example, when the load instruction is executed by a CPU, then we access the level 1 data cache. So I frequently use the dollar sign as the cache. Is it because the pronunciation is the same? So it's a cache and cache. Actually, the pronunciation is the same. So that's why I frequently use the dollar sign as to represent the cache memory, right? Cache, anyway, cache. And then actually, uh, computer, the computer architect researchers use the dollar sign as the cache, okay, right? Anyway, when the load instruction is executed, then firstly, this load instruction accesses level 1 data cache, right? Then what is the result? Actually, there are two kinds of result of these accesses. This access. Firstly, the data can be found. Other result, data is not found. Okay, there are two cases. So actually, until now, until in chapter 4, we just assume that all data are found in the data memory, but actually it's not in the real system. There are two cases. Data can be found or data cannot be found. Okay. So data, if the data is found in the level 1 data cache, then the data is given to the processor. So which means the data is written back to the register file immediately. If so, this is the good case. If data is not found, so not found, then we need to access the lower level memory devices. So in this case, so you can find there are three levels of caches. So usually, our CPUs, desktop CPUs includes the level 1, level 2, level 3 caches. Okay. Then, if the data is not found, then we need to access the low level caches, level 2 caches. So this is also the cache, right? So there are two possible cases, found or not found. Then if the data is not found, then we need to access the low level caches, like level 3 caches. Data is not found in the level 3 caches, then we need to access the main memory, right? So actually, if the data is not found in the main memory, we need to access the storage actually. Okay, but anyway, so until this point, we assume that you can find the data from the main memory, right? So actually, because our computer system includes the memory hierarchy, actually, the memory accesses are performed like this, so hierarchically. So firstly, the CPU accesses high-level memory devices, high-level caches. Then there are two cases, two results, found, not found. Then if the data is not found, then the CPU accesses low-level caches or low-level memory. Okay, that's the operation, the behavior of memory hierarchy. So this case, data is found. This is called the hit. Okay, this is called the cache hit. And then if the data is not found, this is called the cache misses. Okay, hit or miss. So I frequently use the hit or miss in the cache. So hit means that the request data is found in the cache, and the miss represent the request data is not found in the cache. And then if the miss is encountered, then we need to access the low-level cache or low-level memory. Okay, so we define the two different cases, right? Hit or misses. Hit or misses. Then what is the hit rate? Hit rate means the number of hits divided by number of accesses. And then this hit rate cannot be 1, right? Because we can find data or we cannot find data in the cache, right? So hit rate or hit ratio, hit rate is the number of hits divided by number of accesses. Okay. Then what is the good case? What is the good case? If the hit rate is high, then more data are found in the cache, then we can access this data quickly. So if the hit rate is high, then the performance can be improved. Okay. So you need to actually understand this. So in a computer system, we use memory hierarchy, and then because we use the memory hierarchy, then actually when the data are accessed, then there are two cases. There can be two cases, hit or miss. Okay. And then for the miss case, then we need to access the low level cache or low level memory, which means more time, more cycles will be taken, more cycles will be consumed. And then this number of cycles the consumed by the miss event is called the miss penalty. Okay, it's a miss penalty. So more cycles are consumed. It's a penalty for the performance, right? And then obviously miss rate is the number of misses per access. Number of misses divided by number of accesses. Then it is equivalent to the 1 minus hit rate. Okay. So you need to understand the behavior of this memory hierarchy. Okay. Then I briefly explain about the memory technology. So this is the memory hierarchy in our computer system. So memory technology, actually, I mentioned that there are the many different kinds of memory devices, and then these different kinds of memory devices are included in our computer systems. So, the SRAM, DRAM, and then magnetic disk. So this is the hard disk drive. Okay. So you can find the characteristics of these memory devices. SRAM is fast. And then actually SRAM use the more transistors, right? So cost is high. And then we can use the logic process for building SRAM. So that's why the SRAM is embedded in the CPU package. Okay, SRAM is very fast, but it's expensive, so we cannot build large SRAM. Okay, DRAM is the dynamic RAM. Now, as you can see, this is the latency. It means the response time of the DRAM. So DRAM is slower than SRAM, but it's cheaper. Okay, cheaper than SRAM. Magnetic disk, the magnetic disk is extremely slow. Is it because hard disk drive is the mechanical devices, right? So actually, we have motor, and the motor rotates the platter of the hard disk drive. So extremely slow, but it's much cheaper than the DRAM. Okay, so ideal memory means the performance is high, so which means the response time is very low, and then density is very high. But this is ideal, but there is no ideal things in our real world. Okay, so we cannot use the ideal memory, right? So by organizing these different memory devices, then we can build the memory hierarchy like this. Okay, so we can find that. So caches are SRAM. Okay, main memory is DRAM, and then storage is you can use the SSD or hard disk drive as the storage devices. Okay. And then the memory. So actually, the memory is organized as the two dimension, two dimensions. Okay. So address is given, and then we can read the data. So this is the address, and then for each address we can store the data. But we just store the multiple bits per address. So we can just organize the memory like the two dimensions. Okay. And then the number of entries is called the depth of the memory. And then the size of number of bits per this address, one entry is defined as the width. Okay. So we can define the array size as the depth multiplied by width. Okay. So this is the example. And then usually the memory is uh, organized like this. So there is the word line and bit line. And then this is it's called the bit cell, or it's called the memory cell. So we can, it means in this organization, we can store 1 bit of data in this memory cell, right? And then word line is used for activating this memory cell. So this memory cell is activated, which means that this memory cell is connected to the bit line. Then if this memory cell is connected to the bit line, then we can read data from this memory cell. Also, we can store data to this memory cell via bit line. Okay, so the memory is controlled like this. So using the word line, we can activate the corresponding the memory cells. And then if the memory cells are activated, then these cells are connected to the bit line. Then via these bin lines, we can read or write data, okay, to the memory. So the memory is organized like this using the decoder. If the address is given, then we using the decoder, then decoder just to generate the one hot signal. Okay. So if the address is given, only one word line is activated. So for example, if the address 11 is given, then this word line is activated. So this word line is activated, then these memory cells are connected to this corresponding word line. So these memory cells are activated. So these memory cells are connected to the bit line. So we can read for the read request. We can read the bit data stored in these bit cells. Okay, and then we can also, if these bit cells are activated, then we can just write the data to these bit cells. Okay, the memory works like this. So you can just understand that the memory is the two-dimensional the data array. Okay, and then this array is controlled by word line, and then we use the bin9 to read and write data to memory. Okay, so different memories in the solid state memory, then actually we can use the different technologies for these for building these memory cells. Okay, so this is the SRAM memory cell, right? So as I mentioned, the SRAM usually use the more transistors. So and then we can say that SRAM, one bit cell of SRAM uses 6 transistors. So you can find the coupled inverter, two inverters. Two inverters are coupled, and then also you can find the transistor here. So it requires the 6 transistors per memory cell. This is the DRAM. So DRAM is different. So actually, this word line and bin9 is the same. Okay, the organization is very similar. Actually, it's similar. So two-dimensional organization, but only this part is different. DRAM uses one transistor and one capacitor. Okay, so if the word line becomes 1, then this transistor is activated. So capacitor is connected to the bit line. Okay. So we can just store charges, electric charges in this capacitor. Okay. So and then we need to control this operation. So that's why DRAM is slower than SRAM, right? So because it depends on the some signal strength. So this is kind of analog circuit design issues, right? But circuit is different. So you can just understand circuit is different. Okay, so circuit is different, and then so in a DRAM, the strength is low, so it takes longer time to fill this capacitor. Okay, that's why DRAM is slow. Also, it's unstable. Okay, so DRAM looks like this. So only this part is different. Okay. So if we just compare SRAM and DRAM, so SRAM is more expensive, DRAM is cheaper, latency low. It's a response time. Latency is response time. It's high. Density lower, higher. Capacity lower, higher. Volatile. So volatile means that if the electric power is the power supply, so it's a turned off, then data is erased. So it means the volatile. Okay. And then the SRAM is the internal, so it means the on chip. So this is we use the logic processes. The RAM is the external memory. Okay. And then we use the DRAM processes. So I will not explain about the detailed property of DRAM because it's actually we just think the memory is a very simple devices because we using the address, then the data is stored. But DRAM is different. So actually because of these characteristics, we need to control the behavior of RAM with a complex control signals, right? So actually the DRAM is a very complex devices. Okay. Okay, so I will stop here and then thank you for your attention and see you in the next class. 감사합니다.